Hey everybody, now we're going to start volume. This is again part of section 3.6, and this is how to use an integral to find volume. And what we're going to do is actually in a way similar to what we did when we found area. In other words, let, let's just talk you through this here. So we have here, look in the middle. In the middle we have this purple. Look, it kind of reminds me of the end part, like the bell of a trumpet, just cut off. Kind of reminds me of that. Now, I have no formula in geometry how to find the volume or something like that. In geometry, we had formulas for the volume of a cube and the volume of a whatever, but I never had a formula for this random. First, I don't even know what that curve is. I mean, it's a it could be e to the x, it could be whatever 1/x, it could be a lot of things. It could be who knows what. But that's the beautiful thing about calculus. I may not know a geometry formula, but we're going to figure it out anyway. What we're going to do is we're going to take a cross section here. Um, so this is again, we're looking here like on the regular XY plane, and this is that curve just on the XY plane, and we're going from A to B, and this is I'm kind of shading in this area. Now, when we found the area here, if you recall, in order to find the area, back in the previous section, we did the Riemann, trick, the Riemann thing, and we got these thin rectangles. And when we made a lot of these little rectangles, we added them up. We got the area, not the volume, but the area. Area is, what's the difference between area and volume? Area is two-dimensional. Area is like how much paint you need to paint it, and volume is how much water I could fill this thing up with. So so what we're going to do here is if I would take this figure right here and rotate it around, I get this three-dimensional figure right there. So too, if I would take these rectangles and rotate them around, if I look at if I pick any individual rectangle out and I rotate it around, it creates like sort of a little disc. The area of the circle here is just pi r squared. I learned that in geometry. The thickness here, that's my delta x. So the volume of this red disk is going to be pi r squared times delta x. Now I said pi r squared. What is r? R, the radius of the circle, is really the y value of this curve at that particular point, or otherwise known as the f of x value. So really, it's f of. So that leads me to the formula. Drum roll, please. The volume, if I look at these disks all the way through, I get pi times r squared, but r is r is constantly changing. R is equal to the function value, because the height here is the function value at that point. So it's f of x at that point as x is going from A to B, and dx is the thickness. So I'm adding up all different thicknesses. So I get this formula for volume. It's very awesome. And this is where the formula comes from. And now we're going to actually do a problem. Now we're actually going to do a couple of problems using this formula for volume. And again, this is here in the yellow box here is the official, here in the, here in the yellow box is the official formula. Let me just show it to you. The volume of the solid obtained by rotating about the x-axis, the area bounded by the curve f of x, the x-axis, and x equals a and x equals b. That's a fancy way. That's a fancy way of saying that original. This is a fancy way of describing this area right here, because it's bounded by the curve on top. It's bounded by the x-axis on the bottom, and it's bounded by x equals b and x equals a on the sides. So it's just a fancy way of saying that. And the volume is going to be the integral from a to b of pi times f of x squared dx. This is pretty awesome, because even though integrals, we kind of learned them as a two-dimensional thing, but we're going to use the integral technique or technology, whatever you want to say, to find the volume of something that's three-dimensional. That's pretty amazing, because like I say, volume is three-dimensional as opposed to just two-dimensional. So what I want to do now, this is all the theory. Now I want to switch over and actually show you how to work this in a few problems. So I'm going to switch cameras here, and I'm going to set this up. So let me just write. Okay, then we'll go right there, and I'm going to get out some paper. I'm going to write down a problem. So here's our problem. Find the volume of a solid formed by rotating the curve y equals e to the negative x on the interval 0, 1 about the x-axis. And by the way, the word about, in English, I would say rotating around the x-axis, but in math they always say rotating about the x-axis. So you always see the word about when it's a math problem. So I just want you to understand what that means. So let's start by drawing a picture. Let's start by drawing a little diagram here. So I want to draw a two-dimensional. So we draw the two-dimensional picture, and we have, this is y equals e to the negative x. And we're just looking at it from 0 to 1. By the way, the y-intercept is 1 because e to the 0 power equals 1. You don't really, that's not even necessary for the problem, but to solve the problem, but I'm just saying. The y value over here would be e to the negative 1, which means 1 over e. Again, that's not necessary to solve the problem. I'm just pointing that out. So the volume is going to be the integral from 0 to 1 of pi r squared, but like I say, r is equal to the function, so it's e to the negative x squared dx. Now this is equal to, first of all, pi is a constant, so I can pull it out of the integral, 0 to 1. And e to the negative x squared, when you raise a power to a power, you multiply the powers. So this is actually e to the negative 2x dx. Now to solve this integral, I'm going to do a u substitution. I'm going to let u equal negative 2x, and therefore du equals negative 2 dx, which means dx, which is what I have in the integral, is equal to negative 1/2 du. Now, I'm going to, substitute my u substitution. So again, this volume equals negative 1/2 pi. So I'm pulling this negative 1/2 out of the integral. Times the integral from, now I'm not gonna write the parameters here because I'm going to switch back to x and I'll use 0, 1. But I'm not going to use 0, 1 here because it's really, because when x is 0, well, no. When x is 0, u is 0. When x is 1, u is negative 2. But I'm not going to write that because I'm going to just back substitute. So I'm going to kind of leave it blank, leave it uncommitted, very non-committal here. And this is going to be, but now I have e to the negative 2x just becomes e to the u, du. Now dx is du times the negative 1/2. That's where the negative 1/2 came from. Anyway, this is equal to negative 1/2 pi, negative pi over 2 times e to the u. But I want to, before I start evaluating this, I'm going to switch it back to negative pi over 2 e to the negative 2x, evaluated between 0 and 1. And this is equal to, let's see, first I'm going to plug in 1, then I'm going to plug in 0. Negative pi over 2 times e to the negative 2, because it's negative 2 times 1, minus negative pi over 2 times e to the 0, because when x is 0, it's e to the 0. Now, e to the 0 is just 1. So this all equals negative pi over 2 times e to the negative 2, plus, because minus, plus pi over 2. And this is approximately 1.3. It doesn't say what the units are, so I'm going to say units cubed or cubic units. And that is how we do that. That is now, notice I never drew a three-dimensional picture. Partly is because I'm really bad at drawing these three-dimensional pictures. I'll try here. Hopefully I won't butcher it too much. Let's see. Yeah, I'm really bad at these. So here's my original curve. Each disc is going to look like, is going to kind of look like that. It's going to be kind of a circle. I'm going to get something like this, and it's going to be, these are all going to be a bunch of circles. I'm rotating around, and that my friend is the story. Again, I think my three-dimensional drawing is like worse, makes it worse, but that's at least what can I say? I tried. So again, and of course that's 0, 1, and so forth. And this curve is causes y equals e to the negative x, which is what this original curve was. Y equals e to the negative x. By the way, in general, if you want to see great drawings, it's funny. If you want to see a great picture of a two-dimensional graph, I personally like Desmos, which you can get as a website, or you can get it as an app. For three-dimensional drawings, I personally like GeoGebra. It's kind of like it's like combining the word geometry and algebra. So GeoGebra. I like this for 3D graphs, and I like Desmos for two-dimensional graphs. That's just my personal preference. I'm just kind of mentioning it. I get so let's go on to so there you go. So we have the volume now of this sort of bell-shaped figure. This is kind of like what we started with, that belt. The original kind of looks like reminds me of like the bell of a trumpet, sort of. Anyway, that's cut off. Let's go do another problem. So I'm going to load up another problem here. So find the volume of the curve. So we're taking the curve y equals 1 minus x squared, which you experts know that this is a upside down parabola, but I'll draw it in a minute. So I'm taking this curve and we're rotating about the x-axis on the interval -1, comma +1. I'm going to draw the graph right here. This is now that's -1 and that's +1 and that's 1. First of all, how did I know all these numbers? So to find the one up on top, the y-intercept, I plug in x equals 0. So y of 0 equals 1 minus 0 squared equals 1. So that's how I know the y-intercept is 1. For the x-intercept, I turn y into the 0, and I solve for x. So this gives me x squared equals 1, x equals plus or minus 1. So I have +1 minus 1, and this is my region. It's kind of a little mound over there. I drew it. My drawing looks a little bit like a semicircle, but it's not a semicircle. It's a parabola. So it's similar. It's curvy like a circle, but it's not the exact same shape. Anyway, I'm going to rotate this around the x-axis, and as you know, my drawings are pretty pathetic, but it's going to kind of wind up looking like this. And I'm going to draw, so I'm going to have all these little discs here. So it's going to kind of look a little bit like a ball or an egg or something. Again, I'm not a good drawing stuff, but that's what we got. Anyways, so much for my drawings. Let's go to the formula. So the volume is going to be equal to the integral as x goes from -1 to +1 of pi times the pi r squared. The radius is just a function. So it's 1 minus x squared, because that's each at any given x, the radius is 1 minus x squared. And but it's r squared, so I'm squaring it, and that's dx. And this is equal to pi times the integral from -1 to +1 of, now what I'm going to do is I'm going to FOIL this out. I'm going to square this, FOIL it out. So this is going to become 1 minus 2x squared plus x to the 4th dx. Now this is actually pretty easy to integrate. This is equal to, again, it's pi times the integral of 1 is x. The integral of minus 2x squared is minus 2x cubed over 3. And the integral of x to the 4th is plus x to the 5th over 5. And I'm evaluating this between -1 and +1. And this is going to equal, let's say I'm going to make another line. This is going to equal, when I plug in 1, I get 1 minus 2/3 plus 1/5. And then minus -1 plus 2/3 minus 1/5. And when I combine all this, I have 1 minus -1, so that's 1 plus 1 is 2. Negative 2/3 minus 2/3, that's minus 4/3. And 1/5 minus negative 1/5, that's 1/5 plus 1/5 or 2/5. And let's see, let's get a common denominator. The common denominator, I guess, would be 15. So 2 is going to become 30 over 15. The 4 is going to become 20 over 15. And the 2/5 is going to become, I guess, is going to become 6 over 15. And this all combines to by the way, I forgot the pi. Sorry, I hate to now me forgetting pi. I guess I'm on a diet or something. That's why I forgot pi. Whoops, shouldn't have done that. So this is going to be equal to 16 over 15 pi, and that's my final answer. So the volume is going to be 16 over 15, and again, cubic units. So I'm going to write units cubed, and that's my volume, and that is how we do that. Well, everybody, it's been a lovely time. Hope you enjoyed this video as much as I enjoyed making it, and we will see you guys next time.